Hello, everyone. My name is Roy MacPhail, and I'm a master's student under Dr. Hutchinson. Today, I will be presenting on video analysis of fragmental rockfalls and the trends we have extracted from our fragmental rockfall video database.
In this presentation, we'll start by discussing the importance of understanding fragmentation. Part of that is understanding the effects of fragmentation. Part of that is understanding the effects of fragmentation, specifically how fragmentation affects the hazard and risk calculations for linear infrastructure. I'll then go on to speak about the benefits of video analysis when analyzing fragmentation and about how we've gathered our video data so far. Finally, I'll spend the latter part of this presentation discussing the database we have created and exploring some trends that we have extracted so far.
We all know rockfall presents a hazard to linear infrastructure with the potential for property damage and, in extreme cases, loss of life. As such, the hazard must be mitigated. Mitigating systems depend upon an accurate understanding of how the rockfall will travel down a slope. Fragmentation changes most metrics used to design mitigation systems and strategies. This work aims to use photo and video data to expand our understanding of fragmentation so that we can have a more accurate representation of how the rockfall and any fragments travel down a slope. Fragmentation leads to a wider section of linear infrastructure being impacted by the rockfall hazard, and the rockfall path is likely to be significantly altered post-fragmentation. It is true that fragmentation results in smaller rocks at the time of impact and therefore lower kinetic energies. However, when thinking about this, it is important to consider the infrastructure in question. Abbott et al. In 1998 found that it's not always large rockfalls that are most likely to cause derailment of a train. A rockfall with a maximum dimension between 30 centimeters and 1 meter are the primary concern for railways, as they are more likely to lift the wheel. Video analysis allows us to observe fragmentation in real time and in real environments. This gives us the opportunity to track crucial variables that affect the risk hazard calculation, such as the size, speed, and trajectory of objects before and after fragmentation, as well as the number of fragments produced. Conventional analysis of before and after photographs lacks the frame-by-frame tracking of each object that a video enables. This misses the information that is lost between impacts, such as in-air collisions and trajectory, or fragment and rockfall shapes. Moving forward, more video analysis in a variety of geologic settings is needed to understand and model fragmentation.
Here's an example of the clear benefits of video analysis when trying to understand fragmentation. In this video from BC, we can clearly see the spreading effect the fragmentation event is having. We can also see the individual fragments in each frame as they're traveling, and this allows us to identify their trajectories and their shape. This video also shows all the data that is lost with simply before and after photographic data. All of the inner collisions and changes in trajectory.
In order to track trends in fragmentation across geologic settings, slope materials, and slope shapes, we need as many videos from different slopes and geologic settings as possible. Scaling campaigns are a great source of videos because rockfalls are guaranteed to occur at the planned date and time. Traffic control and knowledge of the predicted trajectory allow for optimal safe camera setups for each location. And finally, the camera operator can prioritize events, allowing for short videos of the rockfalls to be captured. Most fragmentation research to date has focused on very controlled environments with rockfall drop tests. These tests have mainly been performed in sedimentary and metasedimentary rocks with structure. This has resulted in a lot of analysis on fragmentation along structure. Crucially, there have not been enough tests in different geological settings to understand the effects of geology on fragmentation. We have created our database to investigate the potential uses of video data to track trends in rockfall fragmentation. We are tracking 66 different variables for each video, including but not limited to the slope characterization, geological, rockfall, and fragmentation information, as well as the presence and effect of vegetation.
In this presentation, I will mainly be discussing fragmentation trends with respect to geological information and rockfall information.
At present, we have received and analyzed 193 videos. In order to understand why fragmentation occurs, it was crucial that we captured video with and without fragmentation. In 21 videos we have, it could not be discerned if the rockfall fragmented. And that was commonly because the video did not capture the complete event. 109 videos had a fragmentation event, where 99 of them were visible and 10 were obscured.
There are a total of 63 videos where the rockfall can be seen throughout the whole video, and we can be sure that no fragmentation event occurs.
We have used this database to track the variables which differed between the videos with fragmentation and without. In order to integrate this work with the development of rockfall modeling software, a video rating system was developed. This is important as only a few videos capture all the required data to enable back analysis and model testing. However, even lower quality videos can be useful for extracting trends with our database. High-quality videos are rated as A and have minimal camera movement or shaking while capturing the complete path of the rockfall and all fragments unobstructed. It is also important that the rockfall is large enough in frame that shape information can be discerned from the video. A B rating is defined as a video with a complete set of information on the rockfall and fragments, but it might exhibit significant movement or have some obstructed frames.
Our database is comprised of 7 Category A videos, 58 Category B videos, 90 Category C videos, and 38 Category D videos.
A-rated videos are harder to capture than B or C videos, and as such, there are very few of these high-quality videos. The database relies on B and C videos where enough information is known to observe trends in fragmentation. The D-quality videos can still be useful when combined with other videos. For example, a D-quality video may highlight the slope geology or structure that will influence the rockfalls in another video on the same slope. Geologic information has not been provided with some of the videos. In these instances, a best guess is made with location data and a visual analysis of the slope. The database does cover all 3 rock types. However, the videos received to date are only representative of a very small number of geological settings, as multiple videos were taken at most settings. It is also important to note that there is not currently enough lithological variety to extract more detailed geologic trends. 65 of the 68 sedimentary rocks are sandstone, 60 of the 70 igneous rocks are andesite, and we have limited lithological information on the metamorphic rocks. As such, the database requires more variety of rockfall videos from all rock types and across as many lithologies as possible to continue exploring trends. Interestingly, the database does not follow the expected frequency magnitude trend of rockfall. There is a flattening of the curve after 5 to 8 centimeters cubed, and we believe this is because scaling is an unnatural rockfall initiation method that focuses on medium-sized rocks that could be hazardous to the road below. It is also important to consider that smaller rockfalls are generally not all captured on a video, as there are too many to account for during the fall event. A key focus of this work is to investigate the factors influencing if fragmentation occurs or not. In the database so far, igneous rocks fragment more often than sedimentary or metamorphic rocks. It is important to assess and understand why fragmentation is occurring, which is something this database can continue to shed light on as it is expanded. Along with rock type, we've investigated the effect of the slope impact material on fragmentation. Research has found that the dissipation of energy is affected by both rockfall and slope materials. As such, it is expected that there should be a difference in occurrence of fragmentation between various slope materials. Rockfall with early impacts on soil or talus were slowed as more energy was dissipated in these impacts than would have been with an impact on rock. Fragmentations occurred significantly more in videos where the initial impact was on rock, and as such, less energy was dissipated early on in the fall trajectory. Here we see only the videos where there was a fragmentation event on the first impact of rockfall on the slope. There were no videos that fragmented on their first impact on talus or the road. 60% of videos with their first impact on rock fragmented on that initial impact, while only 20% of videos with their first impact on soil fragmented on that first impact. The rockfalls that fragmented on their first impact with soil either had a long freefall to build up speed or disaggregated along structure. For our analysis, fragment and rockfall shape is defined by aspect ratios as shown in this ternary diagram. The shape categories have been combined as there are a few videos with rockfall or fragment shapes that do not fall under the compact, platy, bladed, or elongate categories. There are now 4 shape categories: the compact shapes, which include compact, compact platy, compact bladed, and compact elongated, and then platy, which includes platy and very platy, bladed, which includes bladed and very bladed, and elongated, which includes elongated and very elongated. All shape classes are tracked in the database, and this grouping is done only during analysis. It is clear to see that the 3 rock types exhibit different rockfall shape trends across all videos with shape and rockfall data. Igneous rockfall tends to occur in platy and bladed shapes, while metamorphic rockfall occurs in bladed and compact shapes, and sedimentary rockfall is occurring in platy and elongated shapes. Fragment shape is defined as primary and secondary. Primary fragment shape is defined as the most common fragment shape regardless of size, while secondary fragment shape is defined as the second most common fragment shape regardless of size.
In most of the videos captured to date, there is both a primary and secondary fragment shape.
This could be that after fragmentation, 60% of the fragments are compact and 40% of the fragments are bladed. So the primary fragment shape is compact and the secondary fragment shape is bladed. Overall, compact and bladed are the most common fragment shapes across primary and secondary. There is more variety in the primary fragment shapes, whereas the secondary fragment shapes tend to be bladed or compact. Metamorphic rocks fragmented the least, but created the most compact primary fragments. Sedimentary rocks did not commonly fragment into compact primary fragments, but often created compact secondary fragment shapes. Igneous rocks produced more bladed fragments. Compact rockfall shapes fragmented the least, as shown by the far left blue bar in this figure here. When compact rockfall did fragment, they tended to produce compact or bladed primary fragment shapes.
Platy rockfall rarely created compact primary fragments, and elongated rockfall rarely created compact primary fragments or platy primary fragments. Rockfalls with a platy shape tend to produce platy or bladed fragments. Bladed rockfalls tend to produce bladed fragments, and elongated rockfalls tend to produce bladed fragments or elongated fragments. Platy, bladed, and elongated rockfalls tend to fragment at roughly the same percentage. All of these shape categories fragment significantly more often than the compact rockfall shapes. Here we can see that compact and bladed fragment shapes are more common secondary fragment shapes for all rockfall shapes. When we look at the combined primary and secondary fragment shape data, most rockfall shapes produce either compact or bladed as a primary or secondary fragment shape. Often, if the primary fragment shape is elongated or platy, the secondary fragment shape is bladed or compact. Bladed and elongate rockfall produce more compact secondary fragments, while compact and platy rockfall produce a roughly even amount of compact and bladed secondary fragment shapes. Some videos have no secondary fragment shape. This is because all of the fragments are their primary shape. Moving forward, it is important to continue expanding this database and extracting trends from it as it grows. If anyone here has videos of rockfall that could be added to our database, please email myself or Dr. Hutchinson. We will use this information to discern the key variables for modeling of fragmentation, both when fragmentation occurs and how the fragments will behave, as well as their shape and number. This will allow us to develop a fragmental rockfall model, which can then be tested with this data and other data to further improve it. While high-quality videos are needed to test our model, videos of any quality can be added to this database. As the database grows and more information is gathered from different geological settings and lithologies, more trends can be observed. There are several key takeaways from this presentation. Firstly, the fragmentation is not well enough understood. We are currently unable to predict with accuracy whether a rockfall will fragment and how many fragments will be produced, what their shapes are, and what their trajectories will be. All this information is very important as it affects the hazard and risk analysis of rockfall for linear infrastructure. We have learned that video analysis is an excellent tool to investigate fragmentation and is something that is necessary to continue expanding our understanding of fragmentation. The database we created allows broad trends to be discovered that have yet to be fully analyzed because research has focused heavily on controlled trials in specific environments. From our database so far, rockfall shape seems to influence the shape of fragments produced, as well as whether a rock will fragment or not. We have shown that compact rockfalls fragment less often than rockfalls of other shapes. Our database agrees with the research showing that slope material and associated energy dissipation affects the chances of fragmentation, as we have seen where fragmentation is more likely where the rockfall has a first impact on rock. Thank you for listening to my presentation. I would like to acknowledge the Washington, Colorado, California, and Tennessee Departments of Transportation, as well as the BC Ministry of Transportation and Infrastructure for providing the videos necessary to build this database and enable this analysis. Finally, I would like to acknowledge RGHRP and all of its members for making this talk possible. I look forward to any questions people may have. I'll be available in the chat room after this presentation has shown. Thank you very much for your time.